In this video, we'll figure out how to describe the null space in the language of matrix algebra. To this end, I invite you to evaluate the product of these two matrices. Let's call them A and B, and the resulting matrix C. And when you're done with this exercise, you might be surprised to find out that the resulting matrix C consists of all zeros. Well, first of all, this is one of many ways in which matrix multiplication is different from multiplication of ordinary numbers. With ordinary numbers, the only way a product can be zero is if at least one of the numbers itself is zero. With matrices, the result can be zero, even when the matrices themselves are full of non-zeros. Alright, so that's one note. But more importantly, what we need to do now is take a step back and try to understand why this happened. And I think we'll quickly realize that this took place because the columns of the matrix B are in the null space of A. Now, I chose the matrix A to be in its row-reduced echelon form, so it would be very easy to see its null space. And we immediately recognize that the first two columns of B are in the null space of the matrix A. And actually, the third column of the matrix B is 4 of the first plus 3 of the second. I chose it that way on purpose, so it would too be in the null space of the matrix A. And as a result, AB equals 0. Now let's try to understand why being in the null space implies that the result is 0. For that, let's remember the column-wise perspective on matrix multiplication. The columns of this matrix are the linear combinations of the columns of the matrix on the left, where the coefficients come from the matrix on the right. But by the very definition of what the null space is, the null space is the collection of coefficients that produces the zero. So by the very definition of the null space, the result of putting elements of the null space into the matrix on the right is the zero matrix. So this explains how the product of two completely non-zero matrices can be the zero matrix. And that happens when the columns of the matrix on the right are in the null space of the matrix A. And that's actually the only way you could get a zero column in the resulting matrix, if the corresponding column in the matrix B comes from the null space of the matrix A. So given this observation, we can agree that not a bad way to express the null space, and many pieces of software do it just that way, is to combine the basis for the null space, which in this case would be any two of these vectors. Let's of course use these two. Is to combine the basis for the null space into a matrix of its own. And let's call that matrix N. So there you go. This is the matrix representing the null space. And the algebraic expression for this matrix consisting of the elements of the null space is, of course, AN equals 0. Okay, so we're almost done, but I just want to point out that we have to be a little bit careful, because not any matrix that satisfies this relationship necessarily represents the null space. In order to represent the null space well, number one, it has to have just enough columns, and on the other hand, those columns should not be linearly dependent like they're here. Because if you try to use this matrix to represent the null space, that's too many columns. We've seen this before. When we represent linear spaces, we want elements of a basis to figure in our expression. So in order for this matrix, N, to represent the null space, it has to have as many columns as the dimension of the null space, and they have to be linearly independent. If that's the case, we'll say that the matrix N represents the null space. If that's not necessarily the case, then the only thing that this expression implies is that the columns of the matrix on the right belong to the null space of the matrix A. But in any case, this is a very, very concise description of the null space. And that's the power of matrix algebra. Consider this. When we were describing the null space with words, we would have to say a lot of words. We would say that the null space is the collection of all possible sets of coefficients, such that the linear combination of the columns of the matrix A using those coefficients equals 0. In the language of matrix algebra, with the caveats that I mentioned, it's AN equals 0. Now this is a testament to the efficacy of the language of matrix algebra. This is one of the first examples of this kind that we've seen, but we will see many, many more.